Water pollution is one of the most pressing environmental challenges we face today. It affects the quality of water in our rivers, lakes, oceans, and groundwater sources. In this lesson, we'll explore the chemistry behind water pollution, understanding what contaminants enter our water systems and how we can treat them effectively. We'll examine the various sources of pollution, the key parameters that determine water quality, and the scientific methods used to purify contaminated water. By understanding the chemistry of water pollution, we can better appreciate the importance of water conservation and treatment technologies that protect public health and aquatic ecosystems. Water pollution originates from two main categories of sources. Point source pollution comes from single, identifiable discharge points, such as pipes from factories, sewage treatment plants, or industrial facilities. These sources are easier to monitor and regulate because we know exactly where they're coming from. Non-point source pollution, on the other hand, is more challenging to control. It refers to diffuse pollution from large areas like agricultural fields, urban streets, and construction sites. Rain and irrigation water wash pollutants from these surfaces into nearby water bodies. Agricultural runoff carrying fertilizers and pesticides, urban stormwater containing oils and chemicals, and erosion from construction sites are common examples of non-point source pollution. Water contaminants fall into three major categories. Biological contaminants include disease-causing microorganisms such as bacteria, viruses, protozoa, and parasites. These typically come from sewage, animal waste, and untreated wastewater. Chemical contaminants encompass a wide range of substances, including heavy metals like mercury and lead, pesticides used in agriculture, and various industrial chemicals. These can be toxic even in small concentrations. Physical contaminants include suspended solids that make water cloudy or turbid, as well as thermal pollution, where heated water from industrial processes raises water temperature, affecting dissolved oxygen levels and aquatic life. Each type of contaminant requires specific treatment approaches based on its chemical and physical properties. Scientists use several key parameters to assess water quality. Biochemical oxygen demand, or BOD, measures the amount of oxygen that microorganisms need to break down organic matter in water. Higher BOD values indicate more organic pollution. Chemical oxygen demand, or COD, represents the total oxygen required to chemically oxidize all organic compounds in water, providing a broader measure of organic pollution. Dissolved oxygen, abbreviated DO, is the amount of oxygen gas dissolved in water, which is essential for aquatic life. Fish and other organisms need adequate dissolved oxygen to survive. Finally, pH measures the concentration of hydrogen ions, indicating whether water is acidic, neutral, or alkaline. Most aquatic life requires a pH between 6.5 and 8.5. These parameters work together to give us a comprehensive picture of water quality. Heavy metals are particularly dangerous water pollutants because they don't break down and can accumulate in living organisms. Mercury, with the chemical symbol Hg, causes severe neurological damage and kidney dysfunction. It often enters water bodies from coal-fired power plants and mining operations. Lead, symbol Pb, is especially harmful to children, causing brain damage and developmental issues. It comes from old pipes, paint, and industrial sources. Cadmium, Cd, causes bone disease and kidney damage and increases cancer risk. It's released from metal plating industries and battery manufacturing. Arsenic, symbol S, causes skin lesions, cardiovascular disease, and various cancers. It naturally occurs in some groundwater, but is also released from mining and pesticide use. These metals persist in the environment and bioaccumulate in the food chain, making them serious long-term hazards. Eutrophication is a process where water bodies become enriched with excess nutrients, leading to excessive plant and algae growth. Nitrogen compounds, particularly nitrate with the formula NO3- and ammonium NH4+, come primarily from agricultural fertilizers and sewage. These nutrients stimulate rapid algal growth, creating algal blooms that can cover entire lake surfaces. Phosphorus compounds, mainly phosphate with the formula PO43-, originate from detergents and agricultural runoff. Phosphorus is often the limiting nutrient in freshwater systems, so even small increases can trigger massive algal blooms. The real problem occurs when these algae die and decompose. Decomposition by bacteria consumes dissolved oxygen, creating hypoxic or oxygen-depleted zones called dead zones where fish and other aquatic organisms cannot survive. This process demonstrates how chemical pollution can trigger biological changes with devastating ecological consequences. Water treatment occurs in multiple stages, each designed to remove specific types of contaminants. Primary treatment is the first step, involving physical processes. Large debris is removed through screening, and then water flows into sedimentation tanks where gravity causes heavier particles to settle to the bottom, forming sludge. Secondary treatment uses biological processes where microorganisms naturally consume dissolved and suspended organic matter. These beneficial bacteria break down pollutants in aeration tanks, converting them into simpler, less harmful substances. Tertiary treatment involves advanced chemical and physical processes to remove remaining contaminants that earlier stages couldn't eliminate, such as dissolved nutrients, heavy metals, and persistent chemicals. Finally, disinfection kills any remaining pathogenic microorganisms. This can be accomplished using chlorine gas or solution, ultraviolet light that damages microbial DNA, or ozone gas which oxidizes cell membranes. Each stage builds on the previous one to produce clean, safe water. Chemical treatment methods use chemical reactions to remove contaminants from water. Coagulation and flocculation involve adding chemicals like aluminum sulfate, commonly called alum, or ferric salts to water. These chemicals neutralize the electrical charges on suspended particles, causing them to stick together and form larger clumps called flocks that can settle out easily. Chemical precipitation works by adjusting water's pH, typically by adding lime, which is calcium hydroxide. This causes dissolved heavy metals and phosphates to form insoluble compounds that precipitate out of solution as solid particles that can be removed. Advanced oxidation processes generate highly reactive molecules called hydroxyl radicals. These powerful oxidizers break apart persistent organic pollutants that resist conventional treatment, including pharmaceuticals, pesticides, and industrial chemicals. These chemical methods are essential for treating contaminated water that physical processes alone cannot adequately clean. Physical treatment methods remove contaminants without chemical reactions. Filtration passes water through various materials like sand, activated carbon, or specialized membranes. Sand filters trap larger particles, while activated carbon filters use adsorption to capture organic compounds and some heavy metals on their porous surface. Reverse osmosis is a high-pressure membrane process where water is forced through a semi-permeable membrane that blocks dissolved salts, heavy metals, and other contaminants while allowing pure water molecules to pass through. It's highly effective but energy-intensive. Sedimentation relies on gravity, allowing suspended particles to settle naturally in large clarification tanks or basins. The settled material, called sludge, is removed from the bottom while clearer water flows from the top. Adsorption, particularly using activated carbon, works like a molecular sponge where contaminants stick to the carbon's extensive surface area. Physical methods are often combined with chemical and biological treatments for comprehensive water purification. Let's review the essential concepts we've covered. First, water quality depends on measuring and controlling chemical parameters like pH and dissolved oxygen, monitoring biological contaminants such as bacteria and viruses, and assessing physical characteristics like turbidity and temperature. Second, heavy metals and nutrients represent critical contaminants requiring constant monitoring because they persist in the environment and cause serious health and ecological problems even at low concentrations. Third, effective water treatment combines physical processes like filtration and sedimentation, chemical methods including coagulation and precipitation, and biological processes where microorganisms break down organic pollutants. Finally, multi-stage treatment systems ensure communities receive safe, clean water by systematically removing different types of contaminants through complementary processes. Understanding water chemistry is essential for developing effective pollution control strategies and protecting both human health and aquatic ecosystems. This knowledge empowers us to make informed decisions about water use, conservation, and environmental protection.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.